Baby, take my hand. I want you to be my husband, 'cause you're my Iron Man, and I love you 3000. Baby, take a chance, 'cause I want this to be something straight out of a Hollywood movie. Now we're having dinner, and baby, you're my winner. I see the way you smile. You're thinking about the aisle. You reach in your pocket, emotions unlocking, and before you too fast. And all my friends, they tell me they see you're planning to get on one knee. So now I can't stop thinking about you. I figured out all the clues. So now baby, take my hand. I want you to be my husband, 'cause you're my Iron Man, and I love you 3000. Baby, take a chance, 'cause I want this to be something straight out of a Hollywood movie. Fa-da-da-da-da-dum. No spoilers, please. Fa-da-da-da-da-dum. No spoilers, please. Baby, take my hand. I want you to be my husband, 'cause you're my Iron Man, and I love you 3000. Baby, take a chance, 'cause I want this to be something straight out of a Hollywood movie. Baby, no spoilers, please. Fa-da-da-da-dum. No spoilers, please. Ba-da-da-da-da-dum. No spoilers, please. Ba-da-da-da-da-dum. And I love you 3000. Baby, take my hand. I want you to be my best friend, 'cause you're my Iron Man, and I love you 3000. Baby, take a chance, 'cause I want this to be something straight out of a Hollywood movie. See you standing there, and nothing compares. And all I can think is, where is the ring? 'Cause I know you wanna ask, scared the moment will pass. I can see it in your eyes, just take me by surprise. And all my friends, they tell me they see you're planning to get on one knee. But I want it to be out of the blue, so make sure I have no clue when you ask. Baby, take my hand. I want you to be my best friend, 'cause you're my Iron Man, and I love you 3000. Baby, take a chance, 'cause I want this to be something straight out of a Hollywood movie. I see you standing there, and I can't help but stare. I'm ready to bring your wedding ring on the day that we met. I wanted to ask if you would be by my side forever. And though your friends, they tell you they see me planning to get on one knee, I'll make sure it's out of the blue. I promise you have no clue when I ask. Baby, take my hand. I just wanna be your best
Hello, good afternoon, everyone. So, thank you very much for joining us today. So, just a recap on our last few weeks, no? Last 4 weeks of our lecture series was about cybersecurity. And now, we're going back, kaming mga QCSP, no? Kami ulit yung magla-lecture. And for today, yeah, coming from QCSP, ang ating lecturer. I think you already know, sino. But then, let's officially start today's session. So this is the usual thing, no? The session norm. So just engage actively, be open, ask away, and respect everyone. So if you want to ask, you can directly message in the chat box, especially if someone is talking, no? We will have a dedicated question answer portion at the end of the lecture. Ayan. And then, yeah, kumusta kayo guys? So this is the usual question, no? We always ask this every week. Ayan. Ako, ano naman, 1 din and 3. 3 kasi malapit na yung hackathon. Okay? Our first hackathon will be on June 3. Ayan. Sorry, June 6. My bad. June 6. So, I hope to see you guys from Luzon. No? Luzon people, hello. Ayan. So, may mga 1, that's good. At least naka-survive, no? Yeah. 3, that's nice. Sino yung nag-3? Wait, nakita. Okay. Si Mark. Hi, Mark. Bihira yung 3 na yan. So, that's very nice. Yes, so summer season is ending, I think. Sabi ni RJ, it will be rainy day ahead. Yep, yep. Pero I don't think it's very rainy pa, RJ. So, pero if ever, no, bring your weather. I mean, your umbrella and suit for the rainy day. Ayan. So, I think, sabi ni Sir Bobby, no, before we start, maybe we can have a game first. So I prepared a game, no, here in Kahoot. Uh, wait, let me unlock. Ayan. 3 for Kahoot. Okay. So let me share this. 274. Ayan. You can click that link or if you are in your cell phones or mobile phones, yan, you can input that number. So sige, we can wait for a few minutes for you guys to join. Pero the questions are just mainly about the RSA and ECC. Ayan. So hopefully nakita niyo yung lectures na sinend ko dun sa Pre-Shore's channel. So those are important for today's session. Hopefully nakita niyo, no? I know you guys are all busy, pero at least nakita niyo man lang. Yan. Prepare yan ni Sir Bobby. Sige, while waiting, um, I just want to remind you guys that today is the deadline of the X-Qubit. Yan. So until 11:59 today, you will be considered part of the awarding. No? If ever na you didn't submit today, you can still submit on another day, on the next day. Pero hindi na siya magiging, uh, we're not going to consider it for awards. So yung mga nakapag-submit lang on time. Ayan. Sige. Uh, siguro around 4, 4:13, 4:13, we'll start the game. Question. Okay, question from RJ. But considered for completion? Yes. So, yung X-qubit is actually considered for completion, no? Even if beyond 16. So, as long as you submit the X-qubit project, even if beyond the deadline, considered siya as for completion. Okay, so yes, RJ, no? Yes. So, okay lang mag-late submit. Yan. And lahat yan titingnan namin. Okay? Sige, let's wait for 1 minute. We have 62 participants for today, including me. Ayan. Yes, pwede Mark. Pwede ka mag-submit more than one. Yeah. Okay, I think it's 4:13 already and we have 14 participants. Okay, let's check. First question. Can you evaluate that? Now, you're given 60 seconds, so take your time. Open your calculators if you want. May nakapagsagot na. Ang galing. 8. 8 answers. Sige. It's okay. Take your time, guys. 9. Last 4. 11. 12. Last 2. Let's see if tama yung answers nyo. Okay. So the correct answer is 4. Okay, so just raise this to 5 and then modulo it to 14, which is 7 times 2. Yep. Ayan, si Jezreel worshipper. Okay. How about this? Wait, sorry. I think I will skip this. Something's wrong with the question. Wait, I'll skip that. Uh, I forgot to change the answer dito. Okay, sorry. That's not part. Okay. And what should Alice send to Bob to have a secured communication? Is it the plain text, the message, the ciphertext, or the secret? Okay, it should be the ciphertext, no? Kasi if hindi yung ciphertext is just the plain text, makukuha siya ng man in the middle. Okay. If Bob needs to decrypt the ciphertext and Alice used RSA encryption, what will he do? Anong gagawin ni Bob para ma-decrypt yung ciphertext? Eight answers. So, diniscuss to ni Sir Bobby dun sa video. Ayan. Okay, 10 seconds. Okay, it should be the first option. Okay, kasi uh, y- just you just need to raise to your private key. Okay, yung private key ni Bob. Raise the ciphertext to that number, the private key, and modulo it to the public key, which is the PQ. Ayan. I think I'm giving hints for the next question. Ayan. Okay, sinabi ko na kanina. So PQ is the public key. Okay, not the private key. Okay, jazz well worshipper, si anti-jazz, tsaka, okay, si Matt. Congratulations, the three of you. Ayan. So I think some of you have background na sa RSA, no? And that's nice. Sir Bobby, should I play the ECC part? ECC game? Or later na?
Later na lang.
Sige po.
Tapos
Okay po.
let's have a break siguro every hour.
Sige, sir. I'll keep you posted about the time, sir.
Sige.
Apo. Ayan. So, I think to formally start the lecture, we want to introduce, no? I think you guys are all familiar with Sir Bobby already. Ayan. So, Sir Bobby will be talking about the Shor's algorithm. Sorry about the music. Wait. So Sir Bobby will be talking about the Shor's algorithm for today. So there's no other topic but Shor's algorithm. We're going to talk about this algorithm for 3 hours. So without further ado, Sir Bobby, you may now take the floor. Thank you.
Thank you. Can you make my other account
Sure, sir. Opo.
go?
Okay na po.
Okay, thank you. So hello everyone. So our topic today is on Shor's algorithm. It's actually a very long topic, and I will take my time. If ever hindi natin matapos to, don't worry, no? We are going to have a recording of yung hindi natin natapos. Basta makompleto lang natin to, and I don't want to breeze through a topic that is very, very important, especially when you're taking your first course in quantum computing. This is one of the fundamental algorithms in quantum computing. So dalawa lang naman yung fundamental dyan eh. Well, important, fundamental, which is the Shor's algorithm and the Grover's algorithm, both of which can be used to crack encryption. Pero it is Shor's algorithm that will crack yung mga encryption na ginagamit natin, the encryption that we are using. There are only three of them, which is RSA, elliptic curve, and Diffie-Hellman. So unfortunately, that's what we're using right now. And yeah, so as you can see, there are how many PDFs there? 1, 2, 3. There are 5 PDFs now. So we'll start first with the Shor's algorithm, what it is, the theory, and then we are going to discuss the probability of success of decryption when you're using Shor's algorithm. And the next one is so in the first part, while we discuss the Shor's algorithm, we will also touch on the defined quantum Fourier transform. And then on the second part, we are going to derive the circuit of a quantum Fourier transform. So yeah, so after that is we're going to discuss the quantum phase estimation. It's the new way of of formulating the Shor's algorithm, because the original Shor's algorithm was iba yung formulation niya. And it was another person called Alexander Kitaev who used the phase estimation. And fourth will be, we are going to combine how to use the phase estimation with the Shor's algorithm. And lastly, we are going to implement it as a Qiskit circuit. I don't think we are going to complete all of this today. I was when I was starting in quantum computing, it was it's different, no? It's easier to do the math rather than do the programming. Kasi maybe because that's how I started, no? I understood the math, I understood how it works, I understood the magic, but I cannot program. So programming is different. It's a skill. Why? Because when you have this mathematics, you have to know how to translate it into a quantum circuit, and that's different, no? So anyone who understands Shor's algorithm does not necessarily mean they can program it. But anyone who can program Shor's algorithm, it means they understand the math. So yun lang yung nakikita ko dito sa quantum computing, no? So that's why it's important for us to do both. Okay, first one. So let's review first the RSA. So I actually gave you a recording of the RSA, which explains how it works, no? First, how to do it, and then how it works. So let's just review now. Let's just review the period finding, because this is how you crack the RSA. You are going to find the it's like a backdoor to the RSA algorithm. So we know that in RSA, if you have a plain text and then you have a this exponent, which is your so itong plain text na to, so yung exponent na yan C is part of the public key, no? Because you want to send to someone an encrypted message, no? So they publish the public key, so yung exponent at yung itong n, which is the a very big number, composite number, no? Composed of prime numbers P and Q. So so ngayon, so if you have a plain text A, you raise to the C modulo n, then that will be your ciphertext. Yung period finding naman is trying to find the integer r, such the lowest integer r, such that if you raise the ciphertext into this r modulo n, it will give you 1. So ibig sabihin, ano siya na, so yun, is equal to 1, the remainder is equal to 1. So once we know r, once na-compute natin yung r, we can then compute the inverse. The inverse of the ciphertext, no? So the inverse of ciphertext modulo r, kukunin mo yan, no? So C times D, so D prime here is the inverse. When you're able to find D prime, which is the inverse of C modulo R, then you can use the D prime in order to raise the ciphertext to the D prime, and you get the original text now. So I think I mentioned ciphertext. Now this is not the ciphertext. This is the what you call this the exponent, no, which you use to create the ciphertext, which is part of the public key. Okay. Now it works because if you have your ciphertext here, and you raise it to the D, then alam natin na yung B is A to the C, na? B is A to the C. Okay, B is equal to A to the C, and then raised to the D. But C times D, as we have seen earlier, but C times D is equal to 1, no? Or is equal to SR plus 1, no? But since R is a period, then A to the R is equal to 1. So this will become 1, and you'll have times A, no? Kaya B to the D is equal to just the plain text. So that's why period finding works. So therefore, we need to find the value of R in order to decrypt the message. So that is what Shor's algorithm is all about. So we have here, so this function is known as the modular exponentiation function. This is the core of Shor's algorithm. So according to this one here, imagine we can compute the values of f of x, no, where it is equal to d raised to the x modulo n, no, and x is from 0 to some number, which is 2 to the n, no, where n is your p times q. So gagawin mo yan. That's how you find the period. Eh? So you do all of that, no? You do a for loop for x equal to 0 up to 2 to the n, no? And then and then what you do is take a look at the value of f of x. If f of x is equal to 1, then you have found your period. And then you crack the RSA. No? That's how you do it. No? Unfortunately, RSAs are very 2 to the n is a very, very big number. No? It's so hard to imagine it. No? Kasi 2 to, for example, 20, if n is equal to 2048, no? Okay, if you have a 2048-bit encryption, then ano yan, no? 2 to the 2048 is 10 raised to the 600 plus. It's a very big number, no? So if you for loop that according to some research, no, which you can find on the internet, it will take about 300 trillion years to crack the RSA. Kaya matagal talaga siya. And that is the reason why when Shor's algorithm was discovered, quantum computing became a serious subject. Okay, so how do you do this in quantum computing? First, we prepare 2 registers now. So I guess you still remember what the register is now. So the register, no? So it's a group of qubits, no? So the input register will contain the qubits that will be the input to our f of x, and then the output register is the output of your f of x, no? And f of x here is implemented as a function, as a circuit. Now there is because quantum computing is a reversible process, no? So there is a protocol there's a standard protocol for quantum computation that makes it reversible, no? So you have your input register, output register, and then you have your transformation U. And when you apply your transformation to these two registers, what will happen is that the input register will stay the same, okay? Which is, it will stay the same, no? Para siyang identity. And the output register will look like this, no? So whatever is the value of y, you XOR it, no? XOR with the value of f of x. So where f of x is the modular exponentiation function. Now we don't, for the start of any quantum computation is always you generate all possible values. So this means that you apply Hadamard to all of your qubits, no? So apply H to all of the input register, no? Tapos, what will happen is that it will be in superposition. So I guess by now, you should be familiar already with this expression. If you see that, you immediately see that, oh, it's nothing but a superposition of states. Apply Hadamard to all of the input. So, so you have an input register, you generate all possible values because you want to compute the modular exponentiation. So the modular exponentiation is encoded by this U of f, no? So it's a circuit that you implement, and then you make it apply to the qubits, no? And what will happen is that, yeah, so because U of f is a linear operator, it will just be distributed inside you apply it in the summation, no? So it will go inside the summation. And then, if you remember, this is our quantum computing protocol, di ba? So, because yung quantum computing protocol natin, we have, sorry. Hold on. Happened here. So remember the quantum computing protocol, U of x, y is equal to U of f, no? X, y, o plus f of x, di ba? Pero yung y kasi natin 0 eh. No? So 0. Kaya f of x na lang yung natira dyan. And then, ito yung ating modular exponentiation, no? B to the x modulo n. So ito yung magiging, ito yung ating f of x. Okay. So, so after that, well, this is now the state of the output qubit, no? Or the output register. So what we'll do now, the next step is to measure the output register, no? So we measure that, it will collapse into a certain value, no? A very specific value. Let's say it will collapse to a value f of 0. Okay. Now f of 0, so let's assume that f of 0 is equal to x0, x0 now. So what will happen is that the input register, sorry, mali ito. So what will happen is that the input register will now look like this. Okay, so it will now be a superposition of all those numbers whose modulo is equal to f of 0, no? So I hope that's clear now. So, but I will illustrate that later now. So where x of 0 is the smallest value now. So for example, no? meron kang ano, no? Meron kang modulo 2, no? Tapos meron kang 1, 2, 3, 4, no? So if you modulo 2 mo yan, 1, 0, 1, 0, di ba? So, when you measure your output register and you get a 1, okay, then the input register will be a superposition of 1 and 3. Okay, kasi they are the input whose modulo is equal to 1, which is the one that you measured. Okay, so there is a exercise here. So show that M is equal to the floor of 2 to the n over r, no? Okay, so that's something for you to work out. We're gonna use that later. Okay. Now let X be a qubit. So this is now the definition of a quantum Fourier transform. Okay. So let's say that you have a state, no? The state of your qubit is X. Okay, so which means that it's a binary, no? X is it's expressed as binary. So the Fourier transform of that is defined as this one here. Okay. Now this seems to be a very complex looking expression, but that is actually the definition of a Fourier transform, for a discrete Fourier transform. Pero dito applied as into a qubit. And it seems to be complex, no? But later we will find out that this can actually be implemented as a circuit. No? So how to do that, we will find out in our next PDF, no? Which is the one that the next lecture. So anyway, just take a look at this now and try to internalize that kind of expression. So when you see that, that is the quantum Fourier transform. So now that we define what a quantum Fourier transform is, we can then apply it to the state of the input register. So if you remember earlier, so we have an input register and output register. Input register will generate all possible values. Output register will generate all possible values of the modular exponentiation, your f of x. And then you measure the output register, it will give you a certain value, no, of your f of x, no? Now, what will happen is that the input register will now collapse. The state will now collapse into a superposition of all those states whose modular exponentiation is equal to the one that you measured in the output register. No? So kaya siya nagiging ganito siya. Nagiging ganito. It became like this. And then, now that that is the state of your input register, the next thing that you'll do is to apply a Fourier transform, quantum Fourier transform. And the reason why you want to do that is because you are after the period, no? So if you are after the period of a certain thing, then the most natural thing to do is to get the Fourier transform, no? Kasi itong sinabi kong certain thing, this actually is the signal, no? Signal mo, the periodic signal. In periodic signal mo, you apply a Fourier transform, you're actually mapping it the frequency domain, tapos doon mo makikita yung mga frequencies, no? And yung frequency is related to the period of your signal. So that's why we have this. That's why we apply a Fourier transform into your input register. Now, there's a lot of mathematics here, but essentially, you just have to substitute the formula that we discussed earlier. Okay, so if you remember, the quantum Fourier transform is just a summation. This one here, no? So kapag sinubstitute mo yan dun sa dito, and then do some mathematical simplification, you will end up with something like this. Okay. Now, as you can see, the summation is over y, and you have here itong y na to. These are the summation of states. Now, the summation of y states, and these states have a coefficient, and the coefficients, yung coefficient ng states na to are called probability amplitude. No? So this is the probability of getting a specific value of y. No? So if you measure your input register, which is already in this state, no? So after you apply the quantum Fourier transform, it became like that. So a summation of all y's, no? And each y has a specific probability of occurring, no? So when you measure it, of course, the one that you'll measure is the y with the highest probability, no? Now, what we can do in order to visualize this probability is we can simplify this probability amplitude, no? And then draw a graph. So this is what we'll do, no? Ito yung kanina, no? I just rewrote it, no? It's the probability of measuring a specific value of y. Now there is an exercise here, no? This is really nice, no? If you want to, really learn this thing, no? You can get your pencil and paper, no? After this lecture, no? And then you can show that this summation, no, is just equal to this one here. So for simplicity, we just set f to be equal to ry over 2n, no? So ibig sabihin, coming from here, no? So ry over 2n, this becomes your f. And then, if you remember, itong probability amplitude na yan, no? That's the probability amplitude. If you want to get the probability, then you will have to multiply it by its complex conjugate. Now, if you multiply this expression with its complex conjugate, what will happen is that this expression here will become 1. No? So mawawala yan. That will be equal to 1. And what will remain is this one here, no? So that is this expression. Okay. So you're just going to show that this left hand side is equal to sine squared pi fm over sine squared pi f. And then you can use this formula. No? So I also gave a formula. So as a hint. No? Yeah. So it's good that you can you can try get a pencil and paper and try this. So now using the exercise above, the result of the exercise, the probability of getting a specific value of y is this one, no? Now kapag ginraph natin yan, you will notice that ito yung kanyang itsura, no? Yung itsura ng graph niya. And the points of high probability are these integers, no? Kasi maximum yung probability niya, eh, no? So, ibig sabihin, when you measure your input register, it will give you a specific value of y such that the yung kanyang such that it is equal to a integer, no? So you'll get a specific value. Kasi ito, this one is f, no? This actually is f, probability of f. So this one is f value, no? F equal to 2, f equal to 3, f equal to 4, no? So kapag measure mo yung input register mo, you'll get a value of f that is an integer. Now, what is the corresponding value of y? Okay, so you can compute the corresponding value of y because of this formula, no? Ito yung when we set earlier f to be equal to ry over 2n. Okay, now since these are integers, no, from 1 up to 1 to up to r, yan, no? Now there is a so since y is an integer, then this means that the value of y must be close to balik tayo dito, no? So di ba y, di ba f is equal to ry over 2n, no? 2 to the n. We have f. Yan yung measure natin, eh. That's a given. That's the result of measurement. But we don't know what y is. So we have y is equal to itong f na to, j yan, eh. So j 2 to the n over r, no? Yan. So y, no? If you remember, itong expression na to, when we measure the input register, ito yung nakukuha natin, no? Yan. Tapos, now the value of y is integer. It means that the value of y must be close to j 2 to the n over r, no? Diba? So j 2 to the n over r, no? By the way, this one is actually approximately lang yan, kasi itong j 2 to the n over r is not an integer, no? So we want to have an integer that is very close to that, no? So meron tayong theorem in number theory, no? Which states that if you have a rational number p over q, which approximates a real number x, and the distance of that approximation is less than 1 over 2q, no? So this one is a theorem, no? I did not invent that in number theory. Then you can approximate x using a continued fraction expansion, no? So yung continued fraction expansion, I discussed this in the video that I gave, no? Actually, may binigay akong 3 video kay Kyle, no? I hope that you were able to look at it. So yung video na yon, nandun yung RSA, then elliptic curve, and also the and the theory, no? So let me see. Baka wala dun yung continued fraction expansion, but I can explain that now. So in fact, we find that if we find that y is within 1/2 of this value, okay, then by dividing both sides by 2 to the n, we will get this, okay? Now, if you let q be equal to 2 to the n, then this expression here will look like this expression, which means that we can we can use continued fraction expansion of this thing here, y over 2 to the n. Okay. So there is a exercise here. Show that by making the number of qubits in the input register equal to twice 2NO, our estimate for the error is less than 1 over 2 to the n, 1 over 2n squared, no? Which means if you double the number of qubits, then the estimate for error, yung accuracy mo, your accuracy will increase. No? You can also show that. So we can therefore expand y over 2 to the n. So remember, y is the result of our measurement. No? So when we measure the input register, what we get is a value of y. No? 2 to the n. We know 2 to the n. No? So that's the kasi n is the number of qubits. No? So 2 to the n. So if we have if n is 2048, then it 2 to the n is 2 raised to the 2048. So both of them we know. The other one is static, 2 to the n. The other one is dynamic, no, which is the result of measurement. So if we measure the input register, we get y. Then we just expand it, no. When we expand it using continued fraction expansion, now I remember I actually explained continuous fraction expansion using one of the exercises. Yung may exercise akong binigay kay Kyle. Nabigay ko ba sa'yo, Kyle? Did I give you the exercise?
Yes, sir.
Ayun. Nandun yung continued fraction expansion. So by doing that, you do the continued fraction expansion until you get the denominator. No? Until you find the denominator r that is less than n. So once nakuha natin yan, we are going to test whether r is a period. So how do you know r is a period? You get your ciphertext, raise it to the r. Okay, thank you. You raise it to the r, and that will give you a 1. So, ano yan? Then that's the period. Once nakuha mo na yung period, you can then decrypt using this. So you can then decrypt using this method. Okay? Ito yung ating diniscuss kanina, no? Review. So ito example, no? Suppose we have the following RSA parameters, no? N is equal to 3127 and C is equal to 7. If our message is 1907, okay, so meron tayong plain text, no? 1907. So we are going to raise it to the 7 modulo 3127, and it will give you 709. No? Actually, we pad it with a 0, so it becomes 0794. Now, suppose that when we measure the quantum state, no, so ginamitan, we use a Shor's algorithm in order to crack this, no, because we don't know what the factors of 3127 are, no. What's p times q that will give 3127, no? Assuming it's a very big number. We don't know that, no. So ginamitan natin ng Shor's algorithm. We tried to find the period, no, and then what happened is that when we measure the input register, we get a value of y, no. So in order to compute for the value of r, which is the period, no. By the way, just to remind you, ito yung hinahanap natin, di ba? Yung r na yan. So in other words, when we do, magsimula tayo dito, we start with this one, we do continual fraction expansion, what will happen is the end result will look like this, j over r. And r is the one that we are we are that's important for us that we are looking for. Okay, so y over 2 to the n. Okay, so we have y, which is the result of measurement. Now 2 to the n is nothing but 2 raised to the 3127, diba? Okay, and then you do continued fraction expansion, no? So, diba? This one is just equal to 1 plus, sorry. This one is just equal to, this fraction is just equal to 1 over 16777,216 over 1446311. Huh? So you do that until you get something like this, no? And you will, and then what will happen is that once you are able to get that tree of fractions, i-combine mo na naman sila, no? You combine it into a single fraction to get this. 5 over 58. 58 is the one that you're looking for. Okay, so we have only 1 minute, and 58 from our candidate period actually is 58. Then we can test it, no? So we have the 794 raised to the 58 modulo 3127. It gave us 1. Therefore, 58 is a period, no? So once you get the period, you can now compute the inverse of the period, no? Which is using this formula, and you will then see that the inverse is 25, no? So once you get the inverse 25, you get your ciphertext, you raise it to the 25 modulo 3127, and then you get your 1907, which is the plain text that you wanted to find in the first place. Okay, now that's Shor's algorithm. Now that's the theory of Shor's algorithm. So after that, sorry. So what will happen next is we are going to then discuss quantum Fourier transform after our break. Okay, Kyle, we have a break.
Okay po. Thank you, Sir Bobby. So, ayun, I hope you guys are all okay. Ayan, sige. Let's have a break muna. Stretch, and then maybe have some water break then. Very heavy math yung discussion. So, yeah. If you have questions, you can also ask during the break. No? Maybe we can answer some of your questions if merong confusing. Ayun. Let me share my screen. Ay, sige. Wag na. Para nakashare na si Sir Bob.
Okay lang naman, Kyle. I can unshare my screen.
Sige po. Okay.
Unshare. Ayan.
Wait lang po. Na how many minutes sir yung break natin?
Kayo, ilang minutes ba usually yung break
5 minutes, sir?
Okay,
Okay
sige.
lang po. Okay. So we'll be back around 5:05. Thank you, guys. If you have questions, feel free to ask lang. You can also unmute your mic if you want.
Want this to be something straight out of a Hollywood movie, baby. No spoilers, please. I've rejected affection for years and years. Now I have it, and damn it, it's kind of weird. He tells me I'm pretty, don't know how to respond. I tell him that he's pretty too. Can With every passing moment, I surprise myself. I'm scared of flies, I'm scared of guys. Someone please help, 'cause I think I've fallen in love this time. I blinked and suddenly I had a valentine. Bum, ba, da, ba, da, ya, ba, ba, da, ya, ba, 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 ya, ba, ya, ya, ba, 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 ya, da, da, ba, ba, da, ya, ba, 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 ya, ba, ba, ya, da. What if he's the last one I kiss? What if he's the only one I'll ever miss? Maybe I should run, I'm only 21. I don't even know who I want to become. I've lost all control of my heartbeat now. Got caught in a romance with him. Somehow I still feel a shock through every bone when I hear him I love you, 'cause now I've got someone to lose. The first one to ever like me back. I'm seconds away from a heart attack. How the hell did I fall in love this time? And honestly, I can't believe I get to call you mine. I blinked and suddenly I had a Let me be a dreamer, let me float. I can see the whole world from my own little cloud up by the Milky Way. I'll stay there forever and a day. You can't pin me down. I fear all solid ground. I'd rather be alone at tea. Love when nobody's making me. Oh, boys just make me cry. Believe me, I have tried. I've made my rounds, kissed some mouths. Trust me, I don't want a single soul around. Oh, I'm giving up, I'm throwing in my hat.
Sir? Sir Bobby?
Yes, Kyle. Sorry.
Okay. Okay
Kyle
na po
ba?
to continue? Okay. Sige po.
See ya. Okay. Thank you, guys. We share my screen. Okay. Okay. So, that's the Shor's algorithm. And wala na ba? So, akala ko nasa, I thought we were already in the second PDF. But actually, we are still not there, no? We still have to compute the probability of success. So this has something to do with how many times am I going to execute the Shor's algorithm in order for me before I get the period. No? Because quantum computing is a probabilistic, the result is probabilistic. This means that the probability of being correct the first time is not guaranteed na, unless your algorithm, unless probably you're using you're solving the Bernstein-Wasserani algorithm whose probability of success is 1. No? Ibig sabihin, it's certainty. When you use that algorithm, you will get the answer. No? Pero with Shor's algorithm kasi, hindi eh. So Shor's algorithm is one of those examples of algorithms that are known to be hybrid. No? Hybrid means that it's a combination of classical and quantum. No? So quantum is doing the modular exponentiation and the quantum Fourier transform, and classical naman is computing the period. So how lucky do we need, no? In order for the state to collapse to one of these the values of y close to this value, no, j to the n over r. So let's evaluate the probability, no. Suppose we have yj, no, equal to this this expression here, no, plus minus delta j, no. Now, because yj is a um, is a an integer, no? And this one is it's not an integer, may not be an integer, then the closest value is always about 1/2, no? At most 1/2, the closest value to the integer, no? So you remember this one, then ito yung kanina, di ba? Then what we'll do is just to substitute the value of what? Y, you know? Substitute the value of y. No? This is the value of y. Substitute it, and then you'll get this one here now. Okay, you get this one. Okay. So yung mga y natin. Y. So once you get that one, and then you do some simplification, no? Like for example, no? Ito, no? This one is an integer multiplied by pi multiplied by an integer m. So it's a multiple of pi, no? So kapag multiple of pi siya, then according to the behavior of the sine curve, the value of anything multiplied by a multiple of pi will be negative of that thing, no? But because this is sine squared, ibig sabihin, it's gonna be positive. The same goes with this one here, pareho lang. So that's the reason why nawawala sila dito, no? It's gone, no? That's the reason why they are removed, no? In this expression here. So that simplifies to that. Okay, now that one is simplified, we can do another kind of simplification. Take, for example, this denominator. If you think about it, 2 to the n is a very big number. Okay, it's a very big number. So which means this expression here inside sine is small, no? Since it's very small, then we can approximate it using the small angle approximation. So using the small angle approximation, the sine of x, if x is very small, is approximately equal to x. Okay? So that's why we remove the sign. So it becomes x na lang. So next, we can further simplify the numerator. Now, we can approximate, if we can approximate this expression to be equal to 1, approximately equal to 1. Now you might be wondering, where is this equation 6? No? So this equation 6 is this one here. No? If you remember, there was this exercise to show that the what you call this, m is equal to the floor of this one here, or equal to the floor plus 1. No? So, ibig sabihin, floor kasi siya. No? So, ibig sabihin, because m is a integer, di ba? It's either the floor of this expression or the floor plus 1. No? So we can, using this formula, no? So we can approximate, okay, so 2 to the n over r, di ba? So we can approximate, okay, so we can approximate m multiplied by r over 2 to the n approximately equal to 1, no? So this means that this expression here, no? Ano yun? mr over 2 to the n, no? mr over 2 to the n will become 1, no? So what will happen is that pi delta j na lang siya, no? Pi delta j. Now we can further approximate this, no? The sign of pi delta j. Okay, so since delta j is less than or equal to 1/2, no? So as I explained earlier, the nearest integer, no, the nearest integer is always at at most 1/2, no? 1/2, no? So if your integer is 4.6, then the nearest integer is 5, no? But the distance between 4.6 and 5 is 0.4, no? So pwede rin na 4.3, no? The nearest integer is 4. So the distance is 0.3. So as always, the nearest integer is always within 1/2, no? Is always within 1/2. Kaya delta j is within 1/2 na. Okay. Now if we graph this sign of x, no? With if we graph sign of x and we graph 2 to the x over pi, no? This is a line, no? Ito yung line na yan, no? So we have y is equal to 2x over pi, no? You will notice that the line is below the sign of x, no? So in other words, this expression is true, no? Since that expression is true, no, we can then, since that expression is true, and we know, and since delta j is less than 1/2, no, we can then apply it to this expression here, no? Okay, so anong mangyayari dito, no? Yung pi j na yan, that will become this one here, no? Sorry. Yung pi j na yan, this will become this one here, no? 2 pi over delta j, no? And then you do all of the simplification until you find that the probability of getting a successful um, of getting one of these yj, no, is equal to 1 over r multiplied by 4 pi or 4 pi squared. So if you remember, di ba, yung meron tayong graph, no? Tapos naka ano siya, no? may mga peaks and valleys, peaks and valleys, peaks and valleys, no? Now, those correspond to probability. When you measure, when you measure, you will get the probability of getting an integer is high, no? Very high. But it doesn't mean that when you measure, you will get that integer, no? It's possible that when you measure, you will get another value, no? Another value. So, so the probability of getting any one of these integers is this 1 over r over 4 pi squared, no? Now that is approximately equal to 4 over pi squared, no? So 4 over pi squared. So kapag gamitan natin ng calculator yan, 1 divided by 0.405 is equal to 2.3. So if you have a if if you have an experiment and the probability of success is 0.405, then the question is how many times will you repeat that experiment in order to get the first success? So the formula is 1 over 0.4 over 5, or approximately equal to 3 or 2.4. No? So that's how many times you will execute the Shor's algorithm. Okay, no? So that's it. That's the first PDF. Now let's now go to the call this constructing the quantum Fourier transform. So if you remember earlier, meron tayong dalawang quantum register. First quantum the input register will do the superposition of all possible values of your x from 0 to the n minus 1. Tapos yung output register mo naman is it will encode the value of f of x, no? Where x is your input register and f of x is your modular exponentiation. No? So b raised to the x, no? Modulo n. Pagkatapos, we measure the output register, it will give us a specific value of f of 0. And because of that, the input register became a superposition now of all of those numbers whose modular exponentiation is f of 0. Okay, so there are, let's say, m of them, no? And then in order for us to find the period, we now apply the quantum Fourier transform, no? So when we apply the quantum Fourier transform, and then we measure the input register, doon natin gumamit tayo ng continued fraction expansion and then to get the candidate value of your period. And then we tested if it's a period, no, by getting this period and your ciphertext raised to the period modulo n. If it will give you 1, then the one that you computed is a period. Now ngayon, how about the quantum Fourier transform? Now, let's discuss more about the quantum Fourier transform. Okay. Okay, so from the previous session, we have seen the theory on how the quantum Fourier transform is used to crack the RSA. In order to utilize the QFT, we need to implement it, a circuit for it. In other words, we need to program it. When I was just starting in quantum computing, there was no chat GPT. I started 2017. So, I usually learn sa textbook lang. So, but it took me a long time. I had to really spend my vacation just to think about how to program the our Fourier transform. Um, so um, so ito na yung how do we program a QFT, no? Which a very complex looking mathematical expression, no? How do we make that, convert that into a quantum circuit, no? Yung mga squares, no? How do you do that, no? So, in order to learn, no, we learn from the start small, no? So, we were going to make use of the definition first, and then we implement a circuit for a 2-qubit system. So, ibig sabihin, our summation will just be from 0 to 1, no? 2-qubit. And then we are going to generalize this into a multiple qubits, no? And implement a quantum circuit for a 4-qubit system, which we're going to use later to implement a Shor's algorithm. Okay, let's take a look. The basic definition of a quantum Fourier transform. Okay, so that's the definition. Let's take a look at that. No? Summation of e to the 2 pi I xy over 2 to the n. No? So the quantum Fourier transform of the state x is related to e to the 2 pi I, no? Yung x nandyan, and then yung y, no? Where y is summation, no? Summation from 0 to the n minus 1. So ito yung x and y mo. Okay. So let's do the summation, no? So y starts from 0 up to 1, no? So 2 qubit nga eh. 2 up to 1, no? So ito siya, no? Oh, sorry, ano ba? 2 qubit, sorry. Sabi ko. 2 qubit is 2 to the 2 squared, no? So ibig sabihin 4, no? 4. So 0 up to 3. Okay? So 0, 1, 2, 3. Okay? And then yeah, and so we just convert this 0, 1, 2, 3 into their binary representations. Okay? Okay, so far that's very self-explanatory. Now, let's take a look at how to multiply two binary numbers. No? So you have binary x and you have a binary representation of number 3. No? So this is how to express in binary, diba? So this one here is, of course, equal to 3. No? 2 times 1 plus 1. And this one here is also equal to the x, no? Where x is equal to x1, x0, x1 in binary notation. So if you multiply that, you will get this. Okay. So for x1 to x1 to x0, x0. Okay. Pero, ang maganda dito is because we can still simplify this. Why? Because of the exponential, no? So if you do exponential of pi I x dot 3, no? X dot 3, no? Binary multiplication. So what will happen is that it will look like this. However, exponential of 2 pi 2 times pi times I, no, times whatever is the value of x, no, x is either 0 or 1, that can be that is equal to 1, no? That's equal to 1, no? Why is that equal to 1, no? Kaya ang natira dito x1, x0, ito na lang yung natira, no? So ito na lang yung natira, no? Yan. What happened was so very big. Okay. Oh, so big. Marunong So why? Why is it equal to 1? Because exponential of 2 pi I mx is just equal to this. No? This one is 0, di ba? And this one is equal to 1. Kaya equal to 1 siya. Okay. So going back to the Fourier transform, no? And expanding the multiplications, we have, so imagine, so if we go back to this expanded thing here, this one here, no? If we go back here, and then we apply the rules of multiplication, which we have just discussed. For example, apply x dot 3, x dot 2, x dot 1, no? And then simplify. What you will see is that it will then look like this. Yeah. So it will be this expression here, no? So this expression here, we can actually factor it out, no? We can factor it out. Okay, so how do we factor it out? So we can group, no? So what we'll do is this one here, yung 0, ito pala yung 0 dito, no? Andito siya, and then what will happen? What will remain is a 0 and exponential pi I x 0. No? And then you also do for this one here and this one here, no? You group that, and then you will see that there is a common factor, which is this one in under brace, no? Yung mga naka-under brace dyan, that is the common factor. Then you you factor it out, and then you use the what you call this tensor notation, which is this one here. Then you will see that your qubit is now in this form, no? Ito yung qubit na nasa right, ito yung qubit na nasa left, no? So, titingnan natin yan. How do we make those qubit look like this? No? How do we make this, the left qubit into this one, and how do we make the right qubit into this one? No? And then it says here we added a factor of 2 so that it will be obvious that we can use the phase rotation. Okay. So let's this is the part where we have to pay attention. Kasi this is the part where we decipher this equation in order to make this into a circuit. Okay. Now we can take a look, no, at this left side, no? The left-hand side. Left-hand side. So if you take a look at the left-hand side, the question is, how do we get that kind of qubit state? Now it turns out that that kind of qubit state is nothing but the Hadamard. If you Hadamard the first qubit, it will give you that expression. Okay, let's take a look now. So the first factor to the left, from the left, is just the Hadamard gate acting on the first qubit. No? Ano ba yung first qubit dito? Ito ba yung left o ito ba yung right? Is it the left or the right? Okay. So if you take a look, we have exponential of 2 pi I x0. Where is x0? X0 is here, diba? Yan. So in order to get that kind of result, what you'll do is x1 stays the same. So since x1 stays the same, the operator is identity. Since x0 becomes something like this, then the operator is Hadamard. No? Ito. Okay. Hadamard. No? Do you still remember the Hadamard? No? H acting on 0 will give you 0 plus 1 over square root of 2. Okay? And H acting on 1 will give you 0 minus 1 over square root of 2. Now, if you want to combine both of them, what will happen is H acting on X, no? Or X can be 0 or 1, is equal to 0 plus negative 1 raised to the X uh, uh, negative 1 raised to the X 1 over square root of 2. So when X is equal to 0, then you have 0 plus 1 over square root of 2. When X is equal to 1, we have 0 minus 1 over square root of 2. So that's the Hadamard, which is this one here. I forgot the square root of 2. But anyway, negative 1 raised to the x0 is nothing but exponential of 2 pi I x0 over 2. Okay, so that's why it's the Hadamard. Okay, so now we have figured out the first expression. Now let's go to the second expression. Now the second expression is this one here. How did we get that? Huh? So to decipher the second factor, we define the phase rotation. So the phase rotation is a well-known quantum gate, no? So if you use Qiskit, then you can use a phase rotation. It's a well-known quantum gate. That's how you rotate, no? the phase of the qubit. No? And it looks like that. No? That's the matrix. This is the matrix of the phase rotation. Okay. Now, if you apply that to the basis vectors, which are 0 and 1, you will see this. When we apply to 0, it will give the 0, no? Identity. It acts like an identity when applied to 0. However, when applied to 1, it acts like this one here. No? It will do like that. So this is where all of those exponential 2 pi I over n comes from. No? It's the phase rotation. So when you apply a phase rotation, you are essentially multiplying your qubit ket1 by exponential of 2i pi over 2n. No? So that's the phase rotation. Okay, now that we know what the phase rotation is, how can we decipher this? Okay. So let's see how it's derived, no? So the first thing that you'll see here is x1 over 2, no? Kasi ito kasi, you can write this as exponential of 2 pi I x1 over 2 multiplied by exponential of 2 pi I x0 over 4, no? You can write it like that. So the first factor here is nothing but a Hadamard, no? So when you do a Hadamard to your qubit, on the if you apply a Hadamard here and identity here, no? So Hadamard on x1, identity on x0, then you will get this state. Furthermore, if you apply a controlled phase rotation on the first qubit, what will happen? Huh? It will, when you apply the controlled phase rotation on 0 qubit, it will give you 0. No? That's why it's still 0. Sorry. That's why it's still 0. No? But when you apply the phase rotation on the one qubit, this one here, it will multiply it by exponential of 2 pi x1, no? Oh, sorry. Sa x0 nga pala tayo, no? X0 over 4. Okay? Kasi controlled siya eh. Control 0, no? The control is a 0. Ito yung control natin. And yung ating target, and our target qubit is x. Is ito, no? Target qubit. So if the control qubit is x0, then what do you think will be in the exponential? Is it x1 or x0? So it's x0, no? Because if x0 is equal to 0, then there's nothing, it's just multiplying by 1. But if x0 is equal to 1, this means yes. Yes, please. Apply the multiplication, no? E to the pi I, e exponential of 2 pi I, where when x0 is equal to 1 over 4. Right? So, kaya ito siya, no? That's how it looks like this, no? But did you notice anything? Even me, no? Every time I look at this, slide, no, it also confuses me. Why is it confusing? Kasi naka-reverse na. It's reversed. That's why it's confusing, no? So if you get the quantum Fourier transform of x1 x0, what will happen is that the one that we derived, no, it will the one it's equal to this, no, it's equal to this mathematically, but when you implement it as a circuit, it's actually reversed, no? Naka-reverse na siya, di ba? Take a look, no? This one is this one. This one is this one. So if you have, if your, if the result of your operation is reversed, then there is a solution to that, no? You can just apply the swap gate, no? So ito na yung swap gate na yan. Okay. So when you draw it, no? When you if this is your qubit x1 and x0, then you just apply the Hadamard's, the phase rotation, no? Okay. So you can apply the Hadamard, phase rotation, and then Hadamard, and then you just swap it. So kaya ito, mag-swap na yan dito. Okay, and then you'll get the correct implementation of the quantum Fourier transform. So that's how, that's the story of getting, converting your mathematics into the quantum gates. So that's how it works. Of course, there's always a Qiskit counterpart, no? So, kaya nga, learning the Qiskit language is so easy compared to actually making sense of that program. No, it's like, madali yung Qiskit i-program kapag alam mo na, if you already know the theory. So, take a look, no? So yun, no? We know the H, no? This is H, Hadamard, and then this is the syntax of the controlled phase rotation, no? So you do a controlled phase rotation of pi over 2, no? Pi over 2. Okay. So what do you see as well? No? What do you notice? No? The controlled phase rotation doesn't care where the control and the target is, no? Doesn't care. Kaya it looks like a dumbbell because it's the control is in other words, it's what you call that? It's commutative. No? So you can you can reverse the roles of the target qubit, sorry, control qubit and the target qubit. Okay, now, okay, guys, no? So that was the easy part, no? Now let's try to generalize this to n number of qubits, no? Okay. So the quantum Fourier transform of an n-qubit system is generalized by its action on the computational basis. When I say computational basis, these are 0 and 1. 0 and 1. 0 and 1. So, so that is that's how it looks like, no? This is how it looks like, no? This is how the quantum Fourier transform looks like. So if you have n qubits, then it looks like that, no? So pag nakita nyo na yan, if you see that, then you can already see, I have here a Hadamard, I have here a controlled phase rotation, okay? I have here 2 controlled phase rotations, okay? And I have here multiple controlled phase rotations, where we are going to introduce a new what you call that? A new symbol. It's not a symbol, but it's a notation, a new notation. Yung notation na yan, if you see that, that's nothing but the binary fraction. Okay? So for example, x 0.x underscore 0.x m minus 1, that is nothing but x over 2 to the 1. Okay, x over 2. 0 dot the long decimal place now, xm over 2, that is nothing but x m over 2 over 2 to the 2 squared, and so on and so forth. Now, guys, it's very important that I teach you this now, kasi the Bible kasi of quantum computing, no, or quantum information science is the book by, makita ko na lang na, this book here. See that? Okay. Di nyo siguro nakikita, no? Because I have it. But it's the book by Nielsen and Chuang. No? So this uses that kind of notation. So that's the reason why I want you to be able to read that book. No? So that's the reason why I'm introducing this. No? Kasi after this course, no, you should be able to recognize this kind of notation in that book. Okay. Okay, now to understand the derivation, we can restrict n to 3. So when n is equal to 3, then there are how many states, no? 2 to the 3, that is 8. So 0 to 7, no? Okay. Now, if we represent x using its binary expansion, then we can write the above as, okay, itong isang malaking summation na to, no, when you convert it into binary, it is equivalent to 3 summations, no? Where each summation goes from 0 up to 1, okay? So 3 summations. After that, okay, so let X be the base 2 representation. So if we let this be the base 2 representation of X, then the base 10 should look something like this now. Okay. So what I did was just to factor out 2 raised to the 3. And then I got this expression on brackets. And that expression on brackets is can be denoted, no, by this thing here, no, which we discussed earlier as the notation for binary fraction. Now, we will soon encounter this kind of notation, so we need to familiarize ourselves with this notation. Okay, so we have y1, y2, y3 now, multiplied by exponential of 2 pi I xy over 2 cubed. Pero, okay, but y over 2 cubed is equal to this one here. Now, this expression here, no, exponential of that exponential, big exponential is composed of actually 3 exponentials, no, that are multiplied to each other, no. So exponential of 2 pi I x y1 over 2 multiplied by, well, essentially this one here, no. So we just split it, no, into its component factors, and we made this into a tensor product, no? Well, made it explicit kasi tensor product naman talaga yan. So we made the tensor product notation explicit, and then we made it into a more compact form, no? So as you can see, it is the tensor product of 3 different 3 factors, no? So we just made a tensor product like this one, okay, k equals 1 to 3, and then exponential of 2 pi I, this one here. So where the subscript k, okay, and data indicated yk, and then over 2 to the k. Okay, so we have 2 to the 1, 2 to the 2, 2 to the 3. So let's have an exercise. Show that exponential of 2 pi I x over 2 is this one in binary decimal representation. The solution, you just change the x into decimal representation and divide it by 2 to get this one. But we know that 2x will disappear, no? Because it will just become 1, no? Exponential of 2x, it will become 1. Then what will happen is that these 2 factors will remain. Okay. But even this one here, 2 pi x1, 2 pi x2. Okay. Because we multiply by 2 pi, no? Even this one, even the second factor will actually be equal to 1 then, no? So what will happen is that this one will remain. So that's why, and we have shown this to be true. Okay. So when you see something like that, it will look like this. No? So x over 2 will give you dot x3 kasi we are using 3 qubits. So x over 2 will give you dot x3. So what happens if it's x over 8? So if it's x over 8, it will give you dot x1, x2, x3. And that is the derivation. This is the derivation. Okay? So we now go to the definition of a quantum Fourier transform. Because we want to derive that expression that I showed you earlier. No? We want to derive that in a general setting. So if we have a 3-qubit system, then we have the Fourier transform acting on x1, x2, x3, okay, which is equal to this. No? And then using the binary notation, ito yung itsura niya, no? Okay, binary notation. And then this one here, what will happen is that we just applied 2 over 3, no? 2 to the 3. It will look like this. And essentially, when you follow the mathematics, what will happen is that it will look like this. Okay? So we have the 3 summations and one, what you call this, tensor product, no? And then what we do is we change the order of the summation and the tensor product, and guess what happens? What happens is that this one here is just a binomial, no? Kasi the summation is from 0 to 1, no? So that expression here is just a binomial, no? Which is okay, so it's a binomial, no? So y from so how does the binomial look like, no? To look like this, no? So 0, 1, okay? Pero naka-tensor product siya, no? So naka-tensor product, ito, this one, and this one. Okay? And ultimately, it becomes like this. So this is what a 3-qubit quantum Fourier transform looks like. And you can just extend it, no? Generalize it for n number of qubits. No? So using this formula, the Fourier transform of a 4-qubit system looks like this. Okay? It looks like this. So we have here, okay, this one is a Hadamard. This one will give you a Hadamard. You Hadamard x0, x1, and then you apply control phase rotation to x0. You Hadamard x2, apply control phase rotation to x1 and x0. Okay, so that's how you do it. So this is the quantum Fourier transform. So hopefully, you now have you're able to visualize how it's done, no? So how mathematics is converted into a quantum circuit. Okay, so that's how that's why when you do quantum computing, you just don't stop at the theory. No, you go beyond the theory and make it into a quantum circuit. Good, great. Now let's go to the quantum phase estimation. Okay, guys. Actually, we only have 2 more minutes, so probably I can just introduce first the. Okay, Schrodinger equation. Quantum computing is all about quantum mechanics, and the equation, foremost equation in quantum mechanics, the Schrodinger equation. So you have a Schrodinger equation is a first order deterministic partial differential equation that involves instantaneous state of a quantum system. So meron kang quantum system, mga qubits nyo is the quantum system. At any given time, there is a state of that quantum system. Quantum system, may state yan. For every qubit, the state of your quantum system is described by a Bloch sphere. Okay? So when your quantum system evolves, it just rotates on the Bloch sphere. So a time-independent Hermitian matrix H, called the Hamiltonian. The Hamiltonian is one of those things that we measure on a quantum system, and they are called observables. Observables like the energy, the momentum, and the position. So these are, these are properties of your system. So when you measure them, you get a number. And that number turns out to be an eigenvalue of your system. So iba talaga, no? The quantum world is different, no? Here, when we measure in the real world, no, when we measure position, we measure a continuum, no? It can be from here to there and anything in between, no? When we measure energy, no, for example, energy of my, what you call this, no, my power bank, no, it goes from 0 to 100 or 99.9, no, 0.58, no, 1.414, 3. Anyway, it's continuous, it's a real number. However, when you measure the energy of a quantum system, it will give you quantized energy, no? So from one energy level to the next energy level, there is nothing in between. And that's why it's described as a eigenvalue, eigenvalue quantized. No? So anyway, so you have a quantum system and you apply and this is your Schrodinger equation. This one is the time independent Schrodinger equation. Tapos yung Hamiltonian na yan, okay, in time independent Hamiltonian, it has a solution. No? If you are very good at differential equations, you can just get the solution and plug it into the Schrodinger equation to verify that it is correct. So which means that given a state, if your quantum state, your qubits begin at 5, 0, then at any given time, if you let the system be, just leave it there, let it evolve, do not take a look, do not observe, then it will obey the laws of Schrodinger equation, laws of quantum mechanics. And at a certain time t, you will know that it's already at this state, So the state at any given time is expressed by this equation here. But that exponential of the Hamiltonian because the matrix U, the U of t is a matrix now. So you can express this exponential using a Taylor series. Now, if you are familiar with Taylor series now, any function can be expressed as expanded using Taylor expansion. In particular, the exponential function, you express it as a Taylor expansion. Will look like this. Okay? Time check na pala. Okay, sorry. 6:01. So let's go back now. Let's have a 5-minute break. And then after we go back, maybe you can do a Kahoot, Kyle.
Okay, sir. Yeah. Sige po. Thank you, sir. Okay, let's have a break. Again, if you have question, guys, or parang tahimik na kayo. Naka-follow pa ba?
Don't worry, we are going to what you call this, share the video, no? And then you can follow.
Yes po. Yeah. Thank you, sir.
Another lifeless little chat. I'm moving up into a cloud, into my fantasy. And no boy's gonna be so smart as to try and pierce my porcelain heart. No boy's gonna kill the dreamer in me. Some might call me mad, the worst this town has had. I fell right down the rabbit hole. Legends say I fell so fast I lost my soul. Oh, my melancholic days are few and far away. I've had enough, called it off. As far as I'm concerned, this bitch is numb to love. Oh, I'm giving up, I'm throwing in my hat. I can't take another lifeless little chat. I'm moving up into a cloud, into my fantasy. And no boy's gonna be so smart as to try and pierce my porcelain heart. No boy's gonna kill the dreamer in me. Yeah, no boy's gonna be so smart as to try and pierce my porcelain heart. No boy's gonna kill the dreamer in Will you let me come close?
Life goes so fast, I've been living so slow. Let's just leave, do whatever we want to. I don't want no regret or any days.
There's definitely some algebra needed for this implication, but like I said, it's all pretty mechanical. Basically,
I don't want no regret Life goes so fast, I've been living so slow, holding on my past, I just wanna let go. I don't want no regret, no rainy days. When we're out west, we'll only drink French roast, Harlem tomatoes on avocado toast. I don't want no regret, no rainy days. Life goes so fast, I've been living so slow. Let's just leave, do whatever we want to. I don't want no regret, no rainy days. Hey Barbara, maybe I can get you someone. My Sylvia, how can I say that you are mine? Hey Beverly, eyes are blue from what I can see. Hey Stephanie, so you wanna dance with me? I don't care what they say, I'm just trying to be one of the boys. So you can't change your mind, you can never stand alone in the dark. Oh, baby, so dance now, baby. Give it all and I'm gonna start. Dance now, baby. Give it all and I'm gonna start. Olivia, tell me if you are satisfied. My dear Sandra, someday you'll be a superstar, yeah, bow. Hey, my Ramona, eyes are blue from what I can see. Hey, Margarita.
Okay, sir.
Sige. Okay, so I'm just gonna skip this thing here, some theory. So sometimes now, we're talking about quantum computing, X gate, Hadamard gate, controlled phase rotation, and then you ask yourself, so where's the Schrodinger equation here now? How do I know it's a quantum? Where's the Schrodinger equation? Well, it turns out that the Hadamard gates, no, these gates that you use, no, X gate, there is a corresponding Hamiltonian. Once you derive the Hamiltonian, that Hamiltonian is the one that's being used in the Schrodinger equation to have the evolution of your quantum state. So ano siya, my implicitly there is a Hamiltonian. So let's not discuss the deep theory there, no? So let's start with this one here. So we have a Hamiltonian. As I mentioned earlier, a Hamiltonian will describe the energy of your quantum system, and when you measure your system, it gives you discrete packets of energy, and corresponding to each value is called the eigenvalue. Kaya itong lambda na yan, that is called the eigenvalue. And we have also shown that you can, given the Hamiltonian, you can expand the exponential, derive the exponential of the matrix exponential. And that one is also an eigen. That operator also has an eigen value which is equal to exponential of minus I lambda, and it has a corresponding eigenvector, which is the same as the eigenvector. The eigenvector is just the state, no, corresponding to that eigenvalue, eigenstate. So we have a unitary operator with an eigenvector psi, such that u, okay, this operator u acting on psi will give you this eigenvalue equation. Okay, suppose we have that. Then we can define this next thing here. So the if you apply the operator u 2 raised to the j times, for example, if j is equal to 2, then 2 to the 2 is 4, no? So 2 to the j is 4, and therefore you apply u 4 times now. Then what will happen is mathematics is just the eigenvalue raised to the 2 to the j. No? So ganon siya. No? So exponential 2 pi I theta raised to 2 to the j will give you this. Now, there is a question here. What does the transformation look like if you have an input register and an output register? Now we have k, and we have psi, and then there is suppose there is a transformation that converts this into this thing here, no? K as is, no? As if you have a identity, but then what happens is that the output register now becomes u to the k applied on psi. How does it look like? Ano yung itsura niya kapag ginawa nating circuit, no? How does it look like if it's a circuit? So we can write k in terms of its binary expansion. So k, binary expansion. So let us say this one is the binary expansion of k, no? So 2 to the j minus 1 times k j minus 1, no? Plus binary expansion of k. However, this k, if you make this an exponent, it will look like this. Okay? So u raised to the k, if you make convert k into its binary expansion, then it will just be a series of operations u, what else? Okay, so there are how many u's in there? No? There are j number of u's, no? So let's take a look at, for example, any one of these, no? That operator, how does it look like? How do you implement that kind of operator? Okay. How do you implement this now? We know that u will give you this one. Okay. So how does it look like, no? So actually, if the value of kj is equal to 0, then it means don't apply u. Okay? If the value of k, if one of those bits, you made k into its corresponding binary bits back. If the value of that bit is 1, it means apply u. It means multiply by exponential of 2 pi I, no? Theta. Multiply your state. So if that's the case, then this to implement this operator, it's nothing but a controlled u operation. No? Because if the value of k is 0, it means don't apply. If the value of k is 1, it means apply. So it means it's a controlled operation. Okay, so how do you do a controlled operation? Huh? How does it look like in a circuit? How does a controlled operation look like? No? Okay, so it looks like this. Okay, so you have here your qubit. Okay, itong dalawang qubit mo, and these are your controls, no? So this one here is your k. Okay, and this one here is your psi. Okay, so you have a control, no? So it will apply if it's 1, and don't apply if it's 0. So that's how a controlled operation looks like now, mathematically, from a mathematical expression perspective. Ito yung itsura ng from that mathematics, this is how you translate your controlled operation. So now you know how to convert k psi, no? So it's nothing but if you apply u there, it's just k, then u apply to psi, no? With the control on the qubits of k. So suppose we prepare an input and output register, no? So where the input register is a superposition of states, no? As you can see, naka-hadamard yan, no? These are hadamards of 0. Okay, so mula kasi dito na-hatching ako. So hadamard 0, so this is the superposition. Acting, and then we have a tensor product on psi. Okay, so if we apply the operators control k, u raised to the 2 to the k, for k equals 0, 1, no? For 2 qubits, then this is what we have, no? So naging u to the k na yan, no? But u to the k is this one here. Diba? So ito na itsura niya. Okay? So I have an input register which is Hadamard of superposition of states, and I have an output register in the state psi. If I apply control u 2 to the k on this qubits, it will give me this one. Now, take a look. Take a look at that expression. Okay? Ano ba yung expression na yan? I think you have seen this expression many times today, no? So yung expression na yan, what is that, no? So that is called the phase state, no? But you have seen this many times, no? So this is the phase state, ano siya, no? So phi, this is the desired phase state for a quantum phase estimation. So quantum phase estimation is a method in quantum computing where you estimate the eigenvalue. So the quantum phase estimation is very important in quantum chemistry, no? Kasi ano mo yan eh, you have a quantum state, no, which is your chemical simulation, no? And then you want to determine what is the you want to estimate the eigenvalue, no, or the value of your, for example, Hamiltonian on your chemical simulation. So you use a quantum phase estimation. Okay, so 2 pi theta. Now this is this expression here is very familiar. How come? It's very familiar because if we set phi to be equal to x over 2 to the n, then that is nothing but the quantum Fourier transform of x. So yung theta, phi, yung phi na yun, if you set it to x over 2 to the n, then what you have is nothing but a quantum Fourier transform. Now, in order to get the value of x, you just have to apply the inverse quantum Fourier transform. The inverse quantum Fourier transform. So the question is, so what does the inverse look like? Well, it's so easy, no? You just get to invert an operator, you just get its complex conjugate, no? What you call it's not only the complex conjugate, but you get its transpose, no? Conjugate transpose, no? Okay, so ito yun, no? If you have a phase rotation, okay, so let us say you rotated your qubit, in order to undo the rotation of your qubit, just have to apply the inverse of that rotation. But what is the inverse of that rotation? It's nothing but the complex conjugate, the conjugate transpose. Okay, do you remember the transpose? How do you transpose this now? You transpose this by doing it in, putting it in horizontal, no? 1, 0, 1 here, 0 here. And then this one, 0 and e to the 2 pi I over 2 to the n. And then get the complex conjugate, no? The complex conjugate of all numbers, real numbers is equal to itself, but the complex conjugate of this expression here is negative. Kaya andyan siya. So that's the inverse of the quantum of the phase rotation operator. So in other words, if you want to get the inverse Fourier transform, you just have to apply the inverse of that gate. Now, what is the inverse of the Hadamard? Anyone? What's the inverse of the Hadamard? So the inverse of the Hadamard is the Hadamard itself. The Hadamard is its own inverse. Okay. So this is the diagram of the inverse quantum Fourier transform. So the qubit states in left side are initially in the quantum Fourier transform state. Okay, as can be seen on the left, no? So dito yung qubits natin, they are in quantum Fourier transform. That's the initial state. And then in order to get the value of each qubit of the value of x, the bit value, no? So x is x1, x2, x0, x1, x2, di ba? In order to get what the value of x0 is, no? Is it 1 or 0? What's the value of x1? Is it 1 or 0? Okay, what's the value of x2? Is it 1 or 0? In order to get that bit by bit, no? In order to get the value bit by bit, then you just have to apply the inverse Fourier transform, which is this one here. Yeah, H is its own inverse, the inverse of R2. Okay, inverse of R3, inverse of R1. Okay, take note, nasaan yung controls, okay? And then, of course, we swap. Okay, we swap the bit values. Because as we have seen, it's reversed. No? Okay, actually, the probability of success, we already discussed this earlier. So we can now proceed to the fourth PDF, no? Which is how do we combine Shor's algorithm with a quantum phase estimation? Okay. Okay, huwag na tayo mag-review. You already know this, no? Okay, so so Shor's algorithm is about the computing the modular exponentiation. No? Computing the modular exponentiation. Imagine if you do that sequentially, that would take you forever. No? When I say forever, it's more than the age of the universe. No? But with quantum computing, it's able to compute it in parallel. Yun nga lang, you don't know what the answer is. That's the reason why we apply a Fourier transform. Okay, let's start with a review of a quantum Fourier transform. You already know this. Okay, so just take a look at that. You see that kind of notation, that's the quantum Fourier transform of X. And then review, phase estimation, which we have discussed earlier. So we have a Hamiltonian acting on a system psi. It produces an eigenvalue lambda, okay, in the direction of psi. So the eigenvalue, an eigenvector is just a stretch vector. No? It's in the same direction, but stretched by an amount lambda. And then we have also shown that this Hamiltonian, you can get the exponential of this Hamiltonian, and this operator, this operator is the one that ito yung mga gates natin, quantum gates, no? And this operator U has a which looks like that, exponential of minus IH. It has a corresponding eigenvalue, which is exponential of minus I lambda. Okay, so it looks like this. So if we let lambda to be equal to 2 pi times phi, it will look like this. Okay. And we also know that if we define U to be like that, then applying it multiple times, like 2 to the j times, it will look like this. And we have also shown that if we have the input and output register, then to be able to apply this operation, it's nothing but a controlled operation. And the controls are dictated by the value of the qubit, if it's 0 or 1. Okay. So therefore, now we know how to implement this kind of circuit. It only looks like this. Looks like that. Okay. So we have shown that if we have two registers initialized to 0, then and we have input registers initialized to 0 and output register initialized to psi, then if we apply this and since if you apply control u to the k, then it will give you this one here, no? Okay, nawala yung ano, psi. Because it's an eigenvector, then we can just disregard it. Say ano na siya before and after it's the same. So what is important to us is the input register. And then if we let phi to be x over 2 to the n, then this expression here is nothing but the quantum Fourier transform of x. Okay, this one here, x, whatever is x now. So that's the review of quantum phase estimation. Now, let's take a look at the Shor's algorithm. Now, this Shor's algorithm is like the version 2 of Shor's algorithm. No? So the version 1 is hindi natin ginamit, no? And the reason for that is because because I wanted to discuss the quantum phase estimation. So discussing the quantum phase estimation and then applying it to the Shor's algorithm will hit two birds with one stone. So this is the Shor's algorithm. Block box. So we have a circuit now which performs this transformation. No? It transforms jk to j x to the j times k. No? May kulang pa akong ganyan. So andito na pala. Nasa baba pala na. For x co-prime of n. And we have t qubits initialized to 0 and l qubits initialized to 1. So ito siya. Then using Hadamard, we do a superposition. It will look like this. And then when we apply the transformation, when we apply the modular exponentiation, okay? Ito yung modular exponentiation. Okay? Ito. Sorry. Happened to me. This one is the modular exponentiation. Okay, this one here. X to the j k mod n. Okay? Do you remember the modular exponentiation is what we use in order to crack the RSA? Now, it turns out that the modular exponentiation is nothing but quantum Fourier transform of S over R. So itong modular exponentiation, okay, take a look, no? Take a look at the form. X to the j mod n. X to the j mod n is actually equal to this. Assuming that's true, hindi pa natin alam kasi it's not obvious. Why? Why is it like that, no? But let's say that this modular exponentiation becomes a quantum Fourier transform. then using inverse Fourier transform, we can then compute for S over R. Ito. And when we have S over R, then we can use the continued fraction expansion algorithm to compute R. And when we have R, then we have what? Then we can crack the RSA. Okay? We can compute the inverse of R. We can compute the. So I mean, there's an algorithm to crack the RSA. Now, when you get the period. Now, in this session, we want to answer the following question. Why is the output register initialized to 1? Where is the quantum phase estimation used? What is the probability of success, which we already know, no? So we won't care about the third and fourth. We already know it. So ito na lang, why is it initialized to 1? And where is the quantum phase estimation used? Okay, Shor's algorithm. We all know this, no? It can be used to crack the RSA and ACC. It has a subroutine called period finding that uses the quantum phase estimation to find the period. Since the quantum phase estimation, or QPE, okay, if you hear somewhere that QPE, that's quantum phase estimation, estimates the eigenvalue, okay, because we are going to use the quantum phase estimation, then we have to cast our problem into an eigenvalue problem. Okay? So that's really interesting, no? Kasi how can a modular exponentiation become an eigenvalue problem? No? So that's why we are here, no? We want to know. Okay. So this is the definition of the modular exponentiation. So U acting on Y will give you X, Y modulo M. Okay? So that's the basic definition. Okay. So this is now the answer to the question, how can we cast this problem into an eigenvalue problem? So since R is a period, then X raised to the R is equal to 1 modulo M. So which means that U raised to the R, okay, if you apply U R times, then it will just give you this one here. X to the R is equal to 1. So that's why we only have Y. Only Y is left. No? So U to the R applied on Y will give you Y. Then what does that tell you? U raised to the R as an operator is now, you have now cast your problem into an eigenvalue problem. Okay? With an eigenvalue equal to 1, no? But it turns out that there are so many kinds of 1, no? Like, for example, the roots of unity, no? Roots of the 1 are all exponential I, no? Roots of unity. No? Sa high school naman yan. So you should be familiar with the roots of unity. So which is an eigenvalue equation whose eigenvalues are roots of unity. Now, this is your eigenvector. Okay? Yung eigenvector na yan, we are going to verify that that really is eigenvector. No? So in other words, if we apply u to this eigenvector, u to the r to this eigenvector, it will give you a complex number multiplied by this eigenvector. So that's what is known as the eigenvalue problem. Okay, just to make sure, if A is your operator and X is your vector, then if it is equal to this, no, where lambda is a complex number, then this is called a eigenvalue problem. Okay? So ngayon, yung A natin is u to the r, no? So we are going to verify that this thing is indeed a eigenvector. And by doing so, we will also derive the eigenvalue. No? So let's do that. No? Show that this thing is an eigenvector. So by definition of u, so you just apply it to u of s, no? So by definition of u, so ano ba yung u, no? U will give you a so what will happen is that when you apply u, yung x to the k mo becomes x to the k plus 1. Okay? So when you apply u, x to the k becomes x to the k plus 1. So that's the effect of u. And then, as always, no, we try to simplify things by spelling it out, no? Or you write the summation, the actual terms of the summation. You write it. So ito na yun. Okay? Now let's do a trick. No? There's a trick here. We can write this thing here into this thing. No? So in other words, we just multiply it by e to the 2 pi SR and then divide it by e to the 2 pi SR. So that's how it works now. So you multiply it by 1, multiply it by 1. Okay, so multiply it by e to the 2 pi s over r over 2 pi I s over r. So you multiply like that. Huh? And by doing so, you can then factor out this one, and you will get this thing here. However, the last term becomes x0. Why? Because exponential of 2 pi r over r will give you 1. No? This thing is just equal to 1. But since x to the r is equal to 1, diba? By virtue of it being the period, diba? X to the r is equal to 1 modulo n. But 1 can also be written as x to the 0, diba? So therefore, this one here is just equivalent to this one. And this one is equivalent to this one. So now we have shown that U of S is a eigenvector. And this thing here is the eigenvalue. So we now have an we can now use the quantum phase estimation. So since naging eigenvalue problem na siya, we can now use quantum phase estimation to estimate the eigenvalue. Okay? And by doing so, we are able to compute for R. However, if you take a look at the U of S, it also U of S, how do you prepare that state? Because we don't know R, no? In the first place, the R is the one that we are trying to find. Since we don't know R, then we cannot prepare this state. It turns out that there is also a trick to that, no? So if you do a summation of all eigenvectors, okay, and then multiply it by 1 over square root of R, then that is equal to the one state. It's equal to the one state. Okay? It's equal to one state. Now, how do you show that, no? Okay, to show this, so guys, just be patient, no? Because this one is, once you understand this, no? Then Shor's algorithm will not be a mysterious thing anymore to you, no? So to show this, we have to show that this summation is equal to R delta K0. Now this one here is known as the Kronecker delta. It means that is equal to 0 if K is not equal to 0, and equal to 1 if K is equal to 0. No? So yan yung Kronecker delta. No? Ginagamit yan palagi, no? Sa physics, yung Kronecker delta. No? So this is equal to 1 if K is equal to 0, and 0 if K is not equal to 0. Okay? Yan lang yan. So, in other words, yung definition ng Kronecker delta is delta AB is equal to 1 if A equal to B, and 0 if A is not equal to B. Okay? So that's the definition of Kronecker delta. Okay, so sabi dito, what it says here that this summation is actually equal to R if K is equal to 0, no? So in other words, only the first term is not 0, and the first term is equal to R, and the other terms are 0, no? If you do the summation. Why, no? Because when K is equal to 0, then what will happen is that this exponential becomes 1. And if you do the summation of 1 from 0 to R minus 1, no? Then it will give you R. No? There are R copies of 1. No? So if you sum that, then it's equal to R. However, when K is not equal to 0, then this summation is actually a geometric series. And you can get the formula, the geometric sum. The geometric sum is equal to this, no? Where B is this one, and the first term A is equal to 1. So if you apply this geometric sum, okay, if you apply that subgeometric sum, what happens to B to the N? So R yan, R. So B to the R is just equal to 1. So therefore, the numerator is 1 minus 1. So we have the sum is just equal to 0. Okay. So therefore, this formula, we have shown this formula to be true. So in plain English, this formula says that it is equal to R. The first term is equal to R, and the rest of the terms is equal to 0. Okay. So now if you use this formula into the preceding formulas we have, this thing is actually equal to this. Now, since this summation only makes sense if for the first term, kasi for the succeeding terms it's 0, what will happen is that if you expand this summation, you only get the first term. And the first term happens to be this one. Diba? This one is R. This one here is R. Okay? And then square root of R and square root of R will give you R. Cancel, cancel, and then you get 1. Okay, x to the 0 is 1. Okay, so in other words, this is the answer to our question. Why is the output register initialized to 1? Because 1 turns out to be nothing but this formula here. And because of that, we can use the eigenvalue that makes our problem into an eigenvalue problem, and which allows us to use the quantum phase estimation. Okay, so now that we know that the what you call this, the output register is initialized to 1, then let's go back to our algorithm, Shor's algorithm. So initialize first input to 0, output to 1. Okay, and then apply Hadamard's. Okay, so this is what happens no? When you apply Hadamard's. And then apply the control U rotations, no? Control view pala, control view, which is this one here, no? But we know that Uj acting on 1, okay? We know that this one, we know that Uj acting on 1 is equal to Uj acting on this. But we also know the effect of Uj acting on U of S, because that's just its eigenvector, no? So if you apply Uj to Us, then it will give you this one. Okay? And then you do some rearrangement. You rearrange, no? So what will happen is that you rearrange the summation. So the summation of summation according to S is now at the outside, no? And then you put inside the summation to J, then you will have this, no? So if you take a look at that, no? If you imagine that, it's you have R copies of summations. You have R copies of quantum Fourier transform. Okay, so which means that each of the states, no, are now in superposition of the state is now in superposition of quantum Fourier transform. So once you measure the input register, you will get one of these. You will get one of these QFTs, no? So when you measure the input register, it will collapse into one of these, and the qubits will now be in quantum Fourier transform, no? So once they are in quantum Fourier transform, you just apply the inverse quantum Fourier transform. So the equation, the underbrace, is just the quantum Fourier transform of S over R, no? Okay. So apply the quantum Fourier transform will give us the value of S over R now. So when the first register is measured, it will collapse into one of these states now. And each of these state encodes S over R. Because this state is the quantum Fourier transform of S over R. And then you apply the inverse to get to get the value of S over R, and then you use a continued fraction expansion to compute R, and then you use R to decrypt the ciphertext. So that is actually the end of this PDF number 4. No? So next week, we are going to continue with the Qiskit algorithm. No? So ito na yung circuit mismo. No? We're going to use the Google Colab to program the Shor's algorithm now. And then we'll do the post-quantum cryptography and an example of a post-quantum. Okay, back to you, Kyle.
Thank you, Sir Bobby. Ayan. Kumusta ang lahat after the discussion? Ayan. So, siguro we can have a few minutes of question and answer kung meron kayong tanong. So you can raise your hand or chat your question in chat box. Ayan. So meron bang may question sa inyo? Ayan sir, si Piniel. Sige Piniel, you can turn on your mic.
My question si Piniel.
Good evening po, sir. I have a question po. You said po kasi kanina na the Hadamard po is its own inverse. Is it because po when the Hadamard is applied po again, bumabalik po siya sa ket state natin?
Yes.
Ayun lang po. Thank you po for the clarification, sir.
Yeah, so di ba, the Hadamard has a matrix, di ba? Now, if you multiply the Hadamard matrix with itself, you will get the matrix I. No? So, identity matrix. 1, 1, 1 yung diagonal, and 0 yung off diagonal. So, Fanindra has a question. Fanindra.
Yeah, Bobby, it is not related to this session. Just
Okay.
I'm having a curiosity. Recently, I have seen some videos. One of the Chinese lady is telling same mathematics, whatever the mathematics we are using, quantum, the similar kind of mathematics, if we use for the classical computer, it will also work similar to the quantum computers. How much it is true? Maybe you are the localite, you can understand better. That's the reason I'm asking you this question.
So let me see if I heard you correctly. So you're asking if the mathematics of the quantum computation is the same as the classical?
No, there are some algorithms if you use it, and we can make similar. We can get the output of the quantum in the classical itself. We can get it. No need of going for the entanglement and superposition. No need of that much of complexity. She is climbing that one.
Ah, okay. So in other words, there's no need for a quantum computing?
Yes.
Okay, okay, okay. So there is this very, very
A big video which is viral.
yeah. So there is this girl who's very good at algorithms, and then she was able to come up with an algorithm to compute certain uh, linear algebraic quantities that exponentially faster, exponentially fast. So in other words, um, it's possible. Uh, in other words, some people take it to be interpret it to be, oh, because we can do this, then there is no need anymore for quantum computing. Actually, the message, no, the what you call this, the it's not the message, but it's the the way to interpret that, no, is when quantum computer scientists, no, or like for example, people in Google, no, when they do quantum supremacy announcements, no,
Mm.
they should take it with a grain of salt. No, we should take it with a grain of salt. Because when you say something is already has a quantum advantage, no, over the classical algorithms, you really have to make sure that it has that advantage, because it's possible that someone can develop a classical algorithm that is much faster than the one that you just derived. However, it doesn't mean that quantum is already what you call useless. No, why?
Yeah, true.
Because no matter what you do, no matter how much you program your your classical algorithm, like for example, to uh, to do brute force, okay, to for example, to find all possible to be able to find a needle in a haystack. Um, the best case that you can do is to examine each each item one by one. No? When you say needle in haystack, there's no structure. No? Your problem doesn't have any structure that we can exploit. A very good example is finding finding the string that will hash to a certain value. Okay, this is called the hashing now. The only way to do that is to the only way to find is to exhaustively enumerate all of the possible values and input them into the hash function and check if you got the correct hash. So if you do this using a classical computer, you will have to do it one by one. Okay, if you're lucky, you get the first. The first one is correct. If you're unlucky, the last one is the correct one. But on the average, now it's if you have, for example, a million of these of these items, then on the average, 500,000, uh, 500,000, you examine 500,000 entries on the average. That's the best you can do for a classical computer for that kind of problem without any structure. But a quantum
Mm.
computer can do it in square root.
Exponential.
No, for this particular example, can do it in square root because it's Grover's algorithm. Square root, for example, the square root of 1 million is 1,000. Now compare that 500,000 to 1,000. Quantum is still very fast.
So you mean to say, due to the parallel computational capacity of the quantum nature, the quantum is best, but the advantages of classical mechanics we have to take for the algorithmic advantages. Both will reside and it will continue in the future. It will evolve into the faster computers. That is what the conclusion.
So there's only a limit to the classical. It's a mathematical limit, no? So you cannot really go faster than the linear search, or O of n, as they say it.
Order of, yeah.
Yeah, O of n.
Mm.
But quantum is, if you're lucky, you can exploit a what you call this? You can exploit the mathematics. Then you will be able to do it in exponential time, no? But
Yes.
if you're unlucky, then you can do it in quadratic time, which is still much faster than a
Classical.
classical. Yeah. So the lesson there is that whenever quantum computing theorists come up with quantum advantage, they have to make sure first that it's really an advantage.
Bobby, I'm having a query different thing. Maybe I want to ask you, can I ask? It is not related to this subject, some magazine related only. Can I ask the question also, if time permits?
Not
I think maybe we can have a separate discussion with
Yeah.
Sir
So
Bobby. Yeah,
Jose
because
Rafael Matienzo, you're right. That's exactly Erwin Tang, no? She was very young, no? And she was able to come up with an algorithm.
Someone has given reference, Bobby. Sorry, you can
yes,
say.
yeah, that's what he's talking about, Sir Bobby. Yeah.
Oh yeah, Erwin Tang, yeah.
Mm. Ayun. I think we can have another discussion about it if you want, Sir
I'll
Bobby and Fanidra.
keep for
Yeah.
next week. That's fine. No issues for
Yeah,
me.
let's do it next week.
Or maybe not inside the lecture series since this one is for beginners and not for advanced questions. So, ayan. So, I think that's all for today, no, for this question and answer. Um, and there are a lot of more to unpack here regarding that big quantization. That's another field of research. Yeah. So I think we're going to discuss final announcements because it's already past 7. Again, ayan, I'm just reminding everyone na visit the learning management system, answer our assignments. There's just one last assignment that I added. It's about the quantum algorithms last time. No? So it's not including any topics about Shor. So it's just about the Grover, Bernstein-Vazirani, and the theoretical complexity theory in terms of quantum algorithms. Sir Bobby?
Yeah. So Kyle, actually I
Yes, sir.
have a quiz for next week. It will be about elliptic curve cryptography and RSA, no? So ano, ano lang siya, it's a very short quiz, mga 10 minutes lang.
Okay, sir. Sige po. Ayun. For the pre-first discussion, ayan, if you guys haven't understand how RSA and elliptic curve cryptography works, you can visit the hashtag pre-shores discussion channel in our Discord server. So kindly check that out. No, I organized everything in sequential manner. No, so you start from the top up until to the bottom so that you understand how the lecture is actually flowing kapag diniscuss siya. So check that out. Ayan, and then XQBit, no? There's a lot of questions that I'm receiving Until tonight lang ba yung Xqubit? Yung submission, no, yung deadline of submission na until tonight, that means ito lang yung considered for awarding. So meron tayong awarding on May 30 for Xqubit winners. And then if you pass your Xqubit project past beyond the May 16, no, and like past beyond today, meaning it will be still considered for completion of this course, pero it won't be considered for the awarding. Ayan. In speaking of Xqubit, someone asked, kung pwede po bang i-upload sa Google Colab yung Jupyter Notebook file? Yes, pwede. Pwede, no? And then, link yung i-submit, pwede yon. I think that's also easy for us kasi we don't need to run your code locally. So, maybe there are some dependencies that you installed na wala sa local machine namin. So, better rin yan, yung Colab. And then last announcement will be the hackathon. So we're announcing this every week, no? These are the locations, if hindi nyo pa nakita from the last lecture. Okay, now we're going to open it to public. So if you know someone who might be interested, let me know, no? Message it to the Discord server. There is a separate registration for the public, no? So iba yung registration nyo na lecture series participants, iba rin yung sa public. So yes, we opened it to public. Another thing, yan, remember lang na it's still 4 to 5 members per team. Same affiliation, same team. No? That's ideally. Pero if you're individual participant, you don't have any team, so you can just message me, no, answer the registration, and then kami na bahala mag-group sa inyo. Yep. Yeah, for the rules, ayan siya. This will be discussed then during the hackathon proper. And then, kindly answer the pre-registration. No? Konti pa lang yung nag-answer. Nakita ko may around 30 na, pero hopefully mas madami pa mag-pre-register sa inyo. Ayan. So, I'll send the link here. tally.so/rzxwq60. Yan. So kindly visit that, answer the details. Again, if you don't have any members na kilala, you don't have a team, just answer the registration. Yes, Sir Bobby.
You can probably announce na may premyo yan.
As okay. So sabihin ba natin yung amount, sir? Hindi, di ba?
Oh, sabihin mo lang amount. Yung final amount.
Okay. So for the may prizes, no? So we are able to gather funding from different people, different sources. So for the champion, you'll have 7,000. For the first runner-up, you'll have 5,000. For the second runner-up, you'll have 3,000. Yes. So yeah. Hopefully you guys will join. No, I know it's a bit lower, yung prices lower compared to other hackathons. Pero, ayun. For free lang siya. And the point of this hackathon is for us to meet all of you. No? And then, we can build a community, we do networking to each other, and then finally, after all of this session na online, we can meet face-to-face. Ayun. And don't forget, no, yung schedule will be released soon, pero the structure is sa morning, no, starting 8 a.m. Merong mga series of talks about quantum and cybersecurity. At the afternoon, around 1 p.m., mag-start na yung hackathon. Up until 5 p.m. lang siya. Okay? So, you don't need to attend the morning kung malayo kayo. Let's say you're from the Southern Luzon and then you have to go to Nueva Ecija. Don't worry kasi you can just attend the afternoon session if hackathon participant kayo. Okay? So, I think yun lang for today. If you guys have any questions, we cannot answer it right now, pero you can message me in Discord. Ayan. So, see you in the hackathon, hopefully, and see you next week. No? Yep. Sige. I'll stop the recording.